We've been looking at quadratic equations for a while now. We've talked about different properties as well as different ways to solve. We looked at three main ways for solving quadratics, including square roots, factoring, and the quadratic formula. I want to look at another method, completing the square. Typically, if you're choosing a method, typically you will not choose completing the square to solve quadratic equations. However, you will see that this is a nice method to learn because although it may not be overly helpful for solving, it is extremely helpful when changing to vertex form. So if I were to look at this problem here to solve for x-intercepts, my first instinct would be to try to factor this and do factors of 6 with the sum of -4. But as I play around with that, what I will notice is that there are not two numbers that multiply to be 6 and add to be -4. So there is a way to change this or manipulate this equation to make it so it is able to be factored. That's what we're going to call completing the square, and these are going to be our steps. It seems like a lot, but they do flow very nicely together. The first thing we're going to do is we're always going to divide all of our terms so that our quadratic term does not have a coefficient. It does not matter if our linear term has a coefficient, but our quadratic term cannot. Sometimes we will be given equations that we don't have to worry about step 1. If I kind of take the rest of these steps and apply them to example 1 here, using that same equation that we saw up here, I notice on this example I can skip step 1 since x squared has a coefficient of 1. The next thing I'm going to do is get x squared and x alone on one side. So I'm going to go ahead and do that by subtracting 6, giving me y minus 6 equals x squared minus 4x. The next thing I'm told to do here on step 3 is take my linear term and divide it by 2. And then I'm going to square that result. That's doing part A and B of step number 3. I'm then going to, as you can see in step 4, take that result and add it to both sides, giving me y minus 6 plus 4 equals x squared minus 4x plus 4. Now I can factor. Now I can ask myself to find two numbers that multiply to be 4 and add to be -4. We'll notice -2 times -2 and -2 plus -2 works. Notice that that -2 is also showing up right here. It's always going to hold true for that. So instead of saying I have x minus 2 and x minus 2, I'm going to say I have x minus 2 squared, and this becomes y minus 2 over here. That's where we get the name completing the square, because after we factor, we're always going to get a square. If I now wanted to solve this problem, I could go ahead and plug 0 in for y, because I know when I have an x-intercept, that means y equals 0, giving me -2 equals x minus 2 squared. From here, I can go ahead and take the square root of both sides, remembering my plus or minus. Now I'm going to actually bring this over here so I have more room to solve. So I have -2 equals x minus 2 squared. So as I just said, I'm going to take the square root of both sides, remembering my plus or minus. Then I can go ahead and I'm going to do 2 steps in 1. I'm going to take an I out of here, and I'm also going to add 2 to both sides, giving me 2 plus or minus I times the square root of 2 equals x. So notice that this equation is very similar, or this solution is very similar to something I would get when I use the quadratic equation. So essentially completing the square is a way to bypass the quadratic equation. It's just another way of going through that solving process when I can't factor it, a way that I can factor it to get my answers. And if you were to use the quadratic equation on this and simplify as much as possible, these two answers would match up. Let's look at 2 more examples of completing the square. So my steps are going to get covered up, but you hopefully can see them in your notes still. Okay, so first thing I'm going to do is I'm going to divide everything by 2, because remember I said that I do not want that step 1 to have a coefficient on my x squared term. Giving me x squared plus 36 equals -8x. I'm also on step 2 going to make sure that I move my 8x over by adding it and my 36 over here by subtracting it, giving me x squared plus 8x equals negative 36. Now I can take my linear term, step 3, divide it by 2, and square that result. That is what I'm going to add to both sides. I can now factor the left side. Two numbers that multiply to give me 16 and add to give me 8. 4 times 4 and 4 plus 4. Again, notice it's coming from right here, that result I got after doing step A, or part A of step 3. I can also combine these. So I can either say x plus 4 times x plus 4. I can just say x plus 4 squared. Gives me negative 20. If I'm solving for my x-intercepts, I can now go ahead and try to figure out how to get x by itself. So I'm going to take the square root of both sides, giving me x plus 4 equals plus or minus the square root of negative 20. So in order to get x by itself, I'm going to go ahead and subtract 4 from both sides. I'm also going to notice that I can take an I out and rewrite this as square root of 4 square root of 5, giving me x equals plus or minus I square root of 4 square root of 5 minus 4. So x equals, and I don't know why, but I like to have this in the front, so because it doesn't matter what order I add or subtract in, I'm going to move this up to the front. I think just because of how many times I've used the quadratic formula, I've gotten used to seeing solutions in this form. It really doesn't matter where the 4 is. Like I said, it's just my own personal preference. And there is going to be my two solutions. And I do want to look at one final one, so please hang on throughout this, because this one we're going to look at what happens if fractions are involved. So once again, first thing I'm going to do is I'm going to divide everything by 5 to get a coefficient of 1. And I'm going to have x squared equals 6 over 5x plus 2. I want to move this 6 over 5x over so my quadratic and linear term are on the same side, so I'll subtract it off of both sides. Equals 2. Now I'm going to take my b term and divide it by 2. Well, remember that when we divide with fractions, so when I take negative 6 over 5 and divide by 2, remember that's the same thing as multiplying by 1 over 2. That idea behind flip and recip. I'm going to reduce, so this will become 1, this will become negative 3, giving me negative 3/5, which then squared gives me 9 over 25, and that's what I'm going to add to both sides, leaving me with x squared minus 6 over 5x plus 9 over 25 equals 2 plus 9 over 25. Well, now when I try to factor this, I try to come up with two numbers that multiply to be 9 over 25 and add to be negative 6 over 5. I remember in my previous examples, I was just reusing that number from step 3, part A. And if I check, if I were to take negative 3 over 5 times negative 3 over 5, I do get 9 over 25. And if I were to take negative 3 over 5 plus negative 3 over 5, I do get negative 6 over 5. So it does work out, giving me then x minus 3 over 5 squared equals 2 plus 9 over 25. I'm going to do a little bit of scratch work way up here since I'm kind of running out of room, and get a common denominator. So I'll have 50 over 25 plus 9 over 25. So I'm going to get 59 over 25. And I can now solve. My work is, I'm kind of out of room, so I'm going to change colors for my solving process here and see if that helps a little bit. So now when I solve, I'm going to go ahead and take the square root of both sides. I'm going to get plus or minus the square root of 59 over the square root of 25. And then finally, last thing I'm going to do is I'm going to go ahead and find the square root of 25. I know it's 5. 59 cannot be divided by any perfect squares, so I'm going to leave that. But I'm also going to add 3 over 5 to both sides, giving me a final answer of 3 over 5 plus or minus the square root of 59 also over 5. And I can leave it like that. If I wanted to, I could put these together with one denominator. Either way, I'm going to get the same answer. But that is the process for completing the square, and then using completing the square to then solve your quadratic equation.